You know that sound, right? That psst when you crack open a soda and that immediate burst of fizz? Well, turns out that's not just some random bubbling. It's actually a perfect everyday example of a really powerful chemical principle at work. And today, we're going to break it all down. I mean, we've all been there. You leave a soda out for a little too long and it goes from this sharp, bubbly, amazing drink to just a sad, sweet puddle. So, what's actually going on a chemical level that makes it go flat? Well, the whole secret lies in this idea called chemical equilibrium. Think of it like a constant, invisible dance happening inside that soda can. And once you understand the rules of that dance, the whole mystery of the fizz is going to make perfect sense. So, to really get to the bottom of our flat soda problem, we first need to understand what chemists even mean when they say balance. Because, you see, in chemistry, balance isn't this static, unchanging thing. No, it's something way more active. And that brings us to this big idea, chemical equilibrium. Okay, picture a reaction where substance A is turning into B. Simple, right? But what if, at the exact same time, B is turning back into A? Well, when the speed of those two opposite reactions perfectly match up, the system hits equilibrium. From the outside, it looks like absolutely nothing is happening. But on a molecular level, man, it's a constant beehive of activity. And this is the key difference right here between static and dynamic balance. You see a rock on the ground? That's static balance. Nothing's happening, it's just sitting there. But chemical equilibrium is dynamic. It's way more like two people on treadmills walking towards each other at the exact same speed. They're both moving constantly, but the distance between them never, ever changes. That's the kind of balance we're talking about. So the big question is, what happens when you mess with that perfect dynamic balance? Well, luckily for us, a French chemist named Henry Louis Le Châtelier figured that out, and his principle is pretty much the hero of our story today. Okay, so here's the core idea. When a system that's in that perfect dynamic balance gets stressed, and that just means you change something, it doesn't just give up and fall apart. No, it actively fights back to counteract whatever you just did and find a new point of balance. So, the takeaway here is this. Equilibrium systems are resilient. They resist change. You push them one way, and they are going to shift in the opposite direction to relieve that pressure. It's a fundamental rule of how these systems work. Okay, so how do we actually push or stress one of these systems? Well, when it comes to chemical equilibrium, there are three main levers we can pull to make things happen. First, you can change the concentration. That's basically just adding or removing one of the ingredients. Second, and this one's for gases, you can change the pressure by, say, squeezing the container. And third, you can change the temperature, heat it up or cool it down. Each one of these things will knock the system out of whack and force it to respond. Let's start with that first one, concentration. This one's probably the most straightforward. What happens if you take a reaction that's perfectly balanced and just dump in more of one of the starting ingredients? Let's take a look at this classic reaction. On the left side, we have our starting materials, our reactants, hydrogen and iodine gas. On the right, we've got our product, hydrogen iodide. Now that double arrow in the middle, that's the magic symbol that tells us this reaction is in equilibrium. It's going both forwards and backwards at the same time. Okay, now let's apply the stress. Let's just dump a whole bunch of extra hydrogen gas into the mix. The system suddenly has way too much stuff on the left side. So to relieve that stress, what does it do? It pushes back by shifting to the right. It starts gobbling up that extra hydrogen and the iodine to make more of the product, hydrogen iodide, until a new, happy balance is reached. All right, moving on to our second stress, pressure. Now, this one is specifically for reactions that involve gases. And the key thing you need to look at, the only thing that really matters, is how many gas molecules are on each side of that arrow. So let's compare two different cases here. In case one, we've got 2 molecules of gas on the left and 2 on the right. The numbers are equal. So if you crank up the pressure, the system has nowhere to run. Neither side offers an escape, so nothing happens. But now, look at case 2. We've got 2 molecules on the left, but 3 on the right. If you squeeze this system by jacking up the pressure, it's going to try to relieve that stress by shifting to the side that takes up less space, and that's the side with fewer molecules. In this case, it's going to shift to the left. And that brings us to our final stress, temperature. And let me tell you, this one is a total game changer. Why? Well, because changing concentration or pressure just kind of pushes the system around an existing balance point. But changing the temperature, that actually moves the entire balance point itself. It fundamentally changes what the balanced state even is for that reaction. The easiest way to figure out what's going to happen is to just think of heat as if it's an actual ingredient in the equation. So if a reaction needs heat to happen, if it's endothermic, just pretend heat is a reactant on the left side. If you add more heat, you're adding more reactant, so you push the reaction to the right. And if a reaction releases heat, if it's exothermic, just think of heat as a product on the right. Add more heat there, and you'll push the reaction back to the left. Simple as that. Okay, we've learned the rules. We know about equilibrium. We know the 3 main ways to stress it out. Now let's put it all together and finally solve the mystery of our soda can. So here's what goes down at the factory. They take carbon dioxide gas and they force it into the liquid under crazy high pressure. This is a massive stress on the system. So following Le Châtelier's principle, the equilibrium has to shift to relieve that pressure. It shifts hard to the right, dissolving tons and tons of that CO2 gas into the liquid. And then you get home and you pop the top. That hiss you hear, that's the sound of all that high-pressure gas that was trapped in the can escaping into the air. All of a sudden, the stress that was holding all that CO2 in the liquid is just gone. The pressure has just plummeted. So what does the system do? It pushes back. To counteract that massive drop in gas pressure, the equilibrium immediately shifts to the left to try and produce more gas. All of that dissolved CO2 that was in the liquid starts turning back into CO2 gas, trying to replace what was just lost. And that right there is the fizz. That burst of bubbles is not a random thing. It is the sight and sound of Le Châtelier's principle happening in real time. It's all that dissolved CO2 rushing to escape the liquid, trying desperately to reestablish balance in its new low-pressure world. And eventually, the system finds its new balance point at our much lower atmospheric pressure. The physics stops, there's way less CO2 dissolved in the liquid now, and we have a word for that new state of equilibrium. We call it flat. So what started with a simple can of soda actually ends with a really powerful idea: control. By understanding how to stress a system, chemists can push a reaction to create more of whatever they want. We're talking about making fertilizers more efficiently, developing new medicines. I mean, this principle is used every single day in manufacturing all over the world. It really makes you wonder, if you can push and pull on the very balance of the chemical world, what else could you change?